Now we come to discuss about the electromagnetic field propagation or electromagnetic waves propagation. Under the influence of an external field. When you are talking about electromagnetic fields propagation earlier, you are talking essentially about an incident wave that for all purposes see around itself the space time to be isotropic and homogeneous. But the moment there is an electromagnetic field which is held fixed by some external agent, situation is not the same. In fact, if we fix the direction of the electromagnetic field, then rather to be an axis, then around that axis things may be isotropic if we rotate, but if we make a rotation about this axis, it is no more the case. So, in situation like this, one usually loses one or two of the rotational symmetry and might as well lose some of the boost symmetry. So, the number of non-zero generators those contribute to describe your system reduces from what it was originally. Well, that is something about the system degrees of freedom and system symmetries. But is there anything else that one should start bothering? And to address this question, one should in principle start from the propagation of waves in vacuum. When we talk of propagation of waves in vacuum, then the major issue is the number of degrees of freedom that this wave has, and that is 2, not 3, not 4. Usually, when a particular quanta acquires a mass or becomes massive or is massive by construction from the beginning, then the associated number of degrees of freedom for this quanta are usually 3. So, for electromagnetism, can we have a third degree of freedom and make it massive? Any brute force construction of such a term will take us to sacrifice something that is very important, which is called the gauge invariance. So, electromagnetism in vacuum has 2 degrees of freedom. So, any variable that describes the propagation of electromagnetic disturbances better have 2 physical degrees of freedom, and the rest of the 2 degrees of freedom are sacrificed by what is called appropriate gauge choice and the constraints. But the situation changes a little when we have a medium and in a medium a longitudinal component of the excitations of the gauge fields can emerge without sacrificing what we call the gauge invariance. So, the concern is how does this whole thing come about? To talk about that, if we start from the typical action that describes the electromagnetic waves, then apart from the photon kinetic term, which is the first term 1/4 f mu nu f mu nu, there is another piece which is taken as a product of current times the gauge field. Now, I will try to provide here a heuristic argument to go from this action to an equivalent effective description of the photon system, photon and medium system in presence of a background, medium background. And this particular description can be achieved by first noting that any current that one talks about in the contextual reference cannot ignore the fact that the current has to be conserved. In momentum space, it means if you contract the forecurrent with the wave vector or momentum, it should give us 0. Now, a minimalist approach to construct such a form of the current is in terms of a polarization tensor that is contracted with a gauge field tensor A nu. Why is it so? It is because the word identity on the other hand dictates that if you contract a polarization 2-point function, polarization tensor with the wave vector k mu, you must get a 0 irrespective of which direction it is being contracted. So, if we just fix it with another variable that we have for our system, that is the gauge field, if we contract it with, we are very well led with a vector or tensor of rank 1, and now if that is contracted, we get what we have written on the top line here, k mu j mu equal to 0. So, it is a admissible construction that satisfies our requirement of being a current that does not display any anomalous characteristics. And the bonus to this particular approach is there is something called a Kubo formula, which is a celebrated formula that gives the relation between current and the field that naturally gets embedded in this description. But we must say that this is not the only one tensor that you can construct. We can keep on having terms over here by having a tensors of higher rank and multiplied by other vectors, etc. But this is a minimalist approach that we have taken. In the linear regime of the theory that we are interested in, this works pretty well. And so, the effective action can be reconsidered by taking the effective Lagrangian, which is inside the first bracket integrated over the 4 volume to get the action. The equations of motions are derivable from standard procedures, and after that one will get as many equations as there are the number of degrees of freedom. But then at the beginning we initiated this discussion that number of degrees of freedom, if we are moving in a vacuum, then it must be equal to 2 because of gauge invariance. But if you are in a medium and the medium effects are encoded in this object that is written as pi mu nu of x, how do we trace how many degrees of freedom this particular quantity is having? To do that, what is done generally is, whether a system is having some unphysical degrees of freedom or not, is calculated something from what is called a Hessian matrix. It is a 2 by 2 matrix. Sorry, 2 by 2 is not the right way to say it. It is a 4 by 4 matrix. And if this particular matrix is non-invertible, then the system has unphysical degrees of freedom. And in such a situation, there are well laid principles by Dirac-Bachmann. You do a constraint analysis and find out the number of first class constraints and the number of second class constraints, and at the end of the day the number of degrees of freedom n is decided by the formula in equation 4. which states that number of free space variables minus twice the number of first class constraints minus the number of second class constraints. If this number is divided by 2, you will get the number of physical degrees of freedom. Now, when you have a system where there is a quantity which we have defined by pi of mu nu, that is a polarization tensor, and this polarization tensor, if we construct it in the momentum space, it is a scalar function of the wave vectors, their squares, all possible Lorentz invariant variables or covariant variables. It is a function of, apart from temperature, chemical potential, etc., etc. If we go to coordinate space, then what it means is, as the number of or the power of these variables of k square increases, the derivatives power also increases. So, it is a theory now you are dealing with in the a higher derivative theory that you are essentially dealing with. And higher derivative theories, if we consider, you will end up with a equation of higher derivatives. So, for solve them, you need the constants of motion, the integration constants, etc., etc., and things become pretty messy, and it is not unusual to have a unstable, land up with unstable solution. But our objective is to find out the number of degrees of freedom. Unless these extra complications that we have just mentioned comes into play to decide about the number of degrees of freedom of the system, or whether the system has acquired a mass for certain mode or not. So, a heuristic approach should be something or some system that has exhibited this additional modes, existence of these additional modes or massive modes, and if our theory can be mapped to that, then once this mapping is done, we can say that okay, if under certain limit our theory matches with this particular existing theory, then whatever is the conclusion from the existing theory can be borrowed from there and taken to be the verdict for our case. One such theory, it goes by the name of Procka model. The model has its shortcomings, but the outcome is good in the sense that this theory actually produces or predicts the existence of massive mode. So, the effective Lagrangian that we had constructed a while ago, if under some conditions can be mapped onto the Procka model, then we are home and dry. So, the issue is how can we do that? Okay, there is a elaborate way to do it, but that elaborate procedure can be taken up when you have covered few other steps, those are necessary. But before that, we can make some simplistic or simple approach without sacrificing the rigor. to map this particular model of ours to that of Procard. You see, in our model what we have is the extra piece from vacuum given by a quadratic piece in the gauge fields that is multiplied by the polarization tensor pi mu nu, whose arguments are, as we said, all possible values and parameters of the theory. Now, if it so happens that this particular object that goes by the name polarization tensor admits diagonal parts in its matrix description, and they are non-zero and finite. Well, if they are non-zero, they are finite, but it is not necessarily true that this finite quantity has to be real. So, let me say that they are real, and the moment I say that they are real, that means this particular matrix either be real symmetric matrix or a Hermitian matrix, and to be an observable in quantum mechanics or quantum field theory, they better be. So, having evaded the first hurdle, the situation that we have come down to is to say this matrix pi mu nu has at least non-zero elements, real elements in its diagonal form, so that this action that we have written over here in some limit, what is usually called the infrared limit, can be identified to the equation number 14 that we have right before our eyes. And this form of the L effective goes pretty close to what is otherwise described by the Procard-Lagrangian. So, if the Procard-Lagrangian admits mass, this Lagrangian should do that. And not just that, a mass is a measure of an inertia of anything. So, what is a measure or what will be the measure of the inertia here? Well, if you are discussing a wave in a plasma, then the best bet is the plasma frequency. That is the natural frequency with which the waves oscillate. So, the appearance of omega p square here saves the grace of the day. Thank you.